Hello, my name is Charles Taylor. I'm a member of staff at the University of Leeds in the School of Mathematics, and today I'm going to talk a little bit about expectations of random variables. This will include a number of different issues. So first of all, we're going to define what a random variable is and go through concepts of a sample space and probabilities. Then we'll talk about expectations. And then finally, which is perhaps the most interesting part of the lecture or the podcast, is to talk about why in the sample variance do we divide by n minus 1 rather than by n. And that hopefully will be clear after introducing all these concepts. So first of all, what is a random variable? Well, it's pretty much what it says on the tin. So it's something that's random, something that varies. It's not deterministic. It doesn't always come with the same value. It doesn't vary in a way that we can predict it. So it's unpredictable, and it has a number of different features. So usually we'll denote a random variable by a capital letter, and I'm going to use the letter X. It could be another capital letter, but usually fairly consistently is a capital. So in order to describe a random variable, we need two different components. The first is the concept of a sample space. And I'm going to use, for a sample space, a Greek letter omega and a capital Greek omega, which is the sample space of our random variable. Okay, so a sample space is really a list or a description of possible values that the random variable can take. And this could be a very short list. So one example might be that omega is simply the values 0 and 1. So that will be our first example of a sample space. So this means the random variable could take a value 0 with some probability, or the value 1 with some probability. And this is an example where we have a finite list of possible values. It could be a slightly longer list. In fact, it could be an infinite list of values. So we could just put some dots here just to denote that the sample space omega actually has an infinite number of values, in this case any integer, and that would also be a possible sample space for random variable x. So it just says x can take any value, theoretically, of the positive integers. And these two are both examples of discrete random variables. And they're discrete, or the random variable is discrete, simply because the sample space is discrete. So we have, if you like, a countable set of values which constitute the sample space. And just to put an example to this, we could have, in the first case, this 0, 1 might be like an experiment where we toss a coin and we observe the number of heads. So if it's a tail, we observe 0 heads, and if it's a head, we observe 1 head. So this would be a sort of typical sample space for a very simple experiment of tossing a coin. So it's possible also to have a slightly more dense sample space, and another possibility is to consider an interval. In this case, maybe 0 to 5. So what I mean here is, this is the sample space x, or sample space omega, our values x, in which x can take anything in the range from 0 to 5. And I use a round bracket here because we don't include the value 5, and a square bracket because we do include the value 0. So this is an example of an interval for a sample space for the random variable x, and this case we refer to x as a continuous random variable because it can take any value at all in that range. And we treat these two slightly differently, but the first ingredient to describe a random variable is the sample space. So the second item we need is a mapping which takes every element or every item in the sample space to a probability. So what we need now, the second ingredient, is a function, say x equals x, where now little x are values in the sample space. So this is a probability, which is a second ingredient to describe our random variable. And in the case when x is discrete, we can write it exactly as it's written here. This will be a discrete description where we can just write down all these probabilities. In the case when it's continuous, then we would have more generally a function of x. And again, this is for x in omega, and this would be a description for a continuous random variable. So we have these two, if you like, pairings of the different cases. Now these functions could be expressed either in a very general way or as a list. Particularly for the discrete case, we could just write down for every element of the sample space a list. So one example in a discrete setting is to have different values of x and probabilities it takes those values. So let's invent, if you like, a made-up sample space where x can take the values 0 and 1, and then we could associate probabilities with these as a quarter and 3/4. Okay, so this says that the random variable x takes the value 0 with probability a quarter. It takes the value 1 with probability 3/4. You notice I've used a small x for the individual values in the sample space that the random variable can take, and the capital X for the random variable itself, which will always have that form. Little x can then be substituted for 0 or 1, depending on these different situations. So here's an example where we just write down every element in the sample space, and then we associate a probability with those, and we write all of those down in a big long list. An alternative way of expressing this, another example, is to write it in a sort of formula. So now we have the probability that x equals x could be, for example, 2 times a third to the power of x, and we also have to write down the sample space, and we just do it here with the same as before, an infinite list of numbers. And so here we've got a formula which takes every element of the sample space and outputs for that element a probability, and here we have a list. So either of these is acceptable. Of course, we wouldn't want to write down this one in the form of a list because it would be a very long list. We'd run out of whiteboard. We can easily recover the probabilities through a formula like that. And a similar thing will apply in the case of the continuous case. This one will have to have this style of representation because the list is just simply, it's far too big to write down. I'm not really going to go much further into the continuous case. I'm going to stick with the discrete case, but just to point out that that also exists. So we have the concept of a random variable, the concept of a sample space, the concept of a probability, and it's worth just pointing out at this stage that very often random variables are associated explicitly with a probability experiment. So I've already mentioned the idea of tossing a coin where we get a head or a tails. We can associate that with a 0 or 1. We could also think about throwing of a die. In this case, we have values 1 to 6. And in each of these experiments, we can imagine a probability or think about an appropriate probability for that experiment. But note it's not essential to have an experiment in mind. We could just make up values for a sample space and make up values for a probability. But there are some constraints. We can't make up any old values. And the constraints, which if you like are properties of this, are, first of all, that the probability values cannot be negative. Okay, so probabilities have to be non-negative. And the second constraint is that the probabilities, if we add them up over all values in the sample space, and this is a notation for that, the probabilities will add up to 1. Okay, and that's a feature in every case of a random variable. We have a sample space. If we add up the probabilities for all x in the sample space, then we're going to get the answer 1. So this notation here, perhaps a little bit unusual, what it says is this sigma, it's a Greek letter again, capital S, if you like, capital sigma, says that we sum the next thing that follows And we substitute in that sum things which appear in the index here. So x is the index for the sum, and x takes values in omega, which means we substitute each successive value of x in omega, and we add them all up, and the probabilities then will add to 1. So these are constraints for any random variable. And of course, if you look at this one more closely, you can see that not only are the probabilities non-negative, but they must also be less than or equal to 1, because if any of them are bigger than 1, then this one would clearly have to be violated when we add them up, and they're non-negative. So that's the end of the sort of first part, where we're describing a random variable, and we've given the properties of the random variable and described the sample space. And as I said before, we're just going to focus on the discrete case and, as it were, not talk anymore about the continuous one.